So good afternoon, everybody, and welcome. So I will give a presentation on theoretical approaches to correlated quantum dots coupled to superconducting leads. And I should say that this is a summary of work which has been going on in our group in Prague for more than a decade. So there are actually two parts of the group. One is with me at the Charles University, and it's Dr. Martin Žonda, and a little bit also Richard Korytar and Alžběta Karlecová, who is going to have to talk after me. He was my PhD student. And then there is a second kind of branch of the group, which is located at the Czech Academy of Sciences. And it's Petr Zalom, Vladislav Pokorny, and Professor Václav Janiš. And in this past decade, we have been quite intensively collaborating on this topic. So let me just motivate why to study such things. And the motivation is within the context of the present workshop, which means like some kind of quantum technologies. So I'm just going to flash a couple of very recent papers which appeared in, say, past 1 or 2 years on this topic. So it's about qubits, which can perhaps be based on subgap, say, Andreev or Yushba-Rusinov states. Simply so.
We need to share this. For some reasons, we have not shared it.
Okay.
Okay, give me a second. Yeah, please move on. Yeah.
Okay, good. Can I go on, or
Yes,
still a problem?
Yeah. Yes.
Okay, so this is really sort of just a random selection of say qubit-like applications of the physics that I'm gonna talk about. I can't assess at all if these proposals are realistic or not. Nevertheless, they exist in, say, respected journals, so they should not be completely off. Another one, again, qubit based on Yushba-Rusinov states. So this is like 1 year old, and pretty strong group of Katarina Franke, who is an experimentalist, by the way, in Berlin, and Felix von Oppen, who is a theoretician. Again, some question about this Yushba-Rusinov dimers, which seem to be like a potential platform for implementing qubits in these superconducting quantum dots. So this is just really to tell you why perhaps this could be interesting for the present community of say, quantum technologies. So outline of my talk is relatively simple. First, I will actually quite carefully introduce what's known as zero-pi transition and this superconducting single impurity Anderson model, which is a workhorse of our studies. That's like 1/3 of my talk, so don't get too scared. I mean, I will really do a very careful introduction into the topic. Then I will mention some hidden unnoticed identities for this model, which I think these are like the biggest contribution of our group to the community in some sense, because the model is difficult and whatever simplifications are important for the solution. Then I will demonstrate a relatively simple approach, which is second order perturbation theory. And I will show that it gives surprisingly good results, unexpected for just simple perturbation theory. So I will show results for phase boundaries, and also some simple semi-analytical or not semi-analytical, fully analytical theory, which we just came across more or less accidentally, which we call generalized atomic limit. Then I will briefly mention useful phenomenology, which we really made for the experimentalists, because even the second order perturbation theory is still some calculation. So we were able to come up with heuristic formulas, which can be used in certain regimes by experimentalists, which should really simplify the analysis of experimental data. Then, sorry, it's the wrong one. Then I'm gonna show you very briefly, there is a little bit open issue because there are like two names which are used interchangeably between Andreev bound states and this Yushba-Rusinov states. So I will just show you a simple calculation which should relate these two, and then in the end I will really flash like 2 weeks old paper that we have out in PRB, which is on double dot, and there turns out that this generalized atomic limit actually can be transferred to this double dot setup, and it actually works extremely well, which is a pleasant surprise because the double dots are probably more relevant for, say, qubit applications, and having a simple theory which can really describe them nicely is, of course, a very useful thing. So that's the outline. So let me start with a cartoon actually, which should demonstrate the main physics of these correlated quantum dots, and it's the zero pi transition, the Coulomb blockade regime. So just first, maybe let's have a look here. So what we study is a small object. It can be a molecule, it can be some very small metallic grain, it can be a semiconducting nanowire, it can be carbon nanotube, which, I mean, these virus things should be short enough, but short actually means half a micron, which is pretty long as a matter of fact. And still, this system basically behaves as an effective atom, so to speak, meaning that it has discrete single particle levels. And as a matter of fact, one can focus on just single level, which typically can be gated by some nearby electrostatic gates. So in these setups, this single particle energy is actually tunable. And since the object is small, one can't neglect electrostatic interaction between more electrons if they are confined to this spatial region. So there is a finite Coulomb interaction, which we call U here. So I will show you Hamiltonian in a short while, but for now I think intuitively it's hopefully clear. And such an object is actually coupled to two BCS superconductors. So this is shown in here. So this is this quantum dot, which is shown here as the level, so to speak. And here you have the two superconductors, and what is shown in here is their density of states. So there is a superconducting gap. At the Fermi energy, there are the Cooper pairs sitting, and you see this characteristic square root singularities of the BCS density of states. And the question is, okay, if I have such a system, and I make a Josephson junction out of that, which is flanked in with two superconductors. And if you manage to tune the phase difference between them, which can be done by putting this system into some squid setup and tuning the magnetic field, then actually the Josephson current would flow. And it indeed does. Okay, Professor Tepfer might be disappointed that the current is small, which is true. It's in the nanoamp range. Nevertheless, there is a supercurrent. And the question for a theorist is simply, can you predict the supercurrent, its magnitude, and so on and so forth? So it's kind of a routine question. And what is shown in here is the following. So let's assume first this picture where, say, we don't have Coulomb interaction. That can be simply achieved possibly if actually the system is, say, not so small, so that Coulomb interaction is, say, weak, and somehow it does not really influence the physics in some important way. In models, we say that there is no Coulomb interaction, which is an approximation, but nevertheless. And then we just want to kind of calculate in the lowest order of perturbation theory in tunnel coupling between the superconductors and this quantum dot, what will be the supercurrent. And it's a tunneling problem. And actually what you need to achieve is to get this Cooper pair sitting on the left side to the right side. And this process is just Josephson tunneling, which is responsible for the Josephson current. So let's see what we can do about it. And what is shown in here are actually sort of parts of the quantum mechanical amplitude which achieves this state. So what you see in here is that, okay, first this guy must go out because there can't be more than simply two electrons on the dot. And if there are two, there is no chance to get there anything else. So this guy must go out, and this Cooper pair breaks, and this guy is pinned down, just replaces the original one. So the intermediate state is this one. So the Cooper pair was split on the left side, and there is also an unpaired electron on the right side. So that's an intermediate virtual state. And then we can achieve what we want by two more steps, which are that simply this electron goes out, and this electron replaces him. And in the end, the final state is exactly what we wanted. So the dot is in the same state, and the Cooper pair just transferred from here to here. And this can be actually written down in formula. It's called the co-tunneling order, which is like force order, because there are these 4 processes in tunneling in the perturbation theory and so on, and you get some number. Okay, whatever. Now imagine kind of the opposite case as for the Coulomb interaction. So in this situation, there was U0, and by the way, there are like actually 6 processes which one needs to sum up in the case of 0 U. This is just one of them. If we assume actually a very strong Coulomb interaction, which can also happen that it's really so strong that in practice you can say there is no chance that 2 electrons, of course with opposite spin because it's the same level, so by Pauli principle the only chance to put 2 electrons is that they have opposite spins. So no, there is no chance that these 2 electrons, even so allowed by Pauli principle, can sit there because the Coulomb interaction is so strong that simply you can't press the second electron there. Such a regime can be achieved as well experimentally. And if you look at the same problem, so getting the Cooper pair from one side to the other side, then one has to do it slightly differently, because first of all, as I said, there can be only 1 electron. So let's assume that there is 1 electron sitting on the dot, and the processes are now slightly different. So this guy must go out simply because there can be just 1 at maximum. Then this guy goes in. And then you just finish it that this goes out and it goes in. And we are left with something which looks like the sort of the original situation transferred to the right side, but that's actually not true, because if you look here, the Cooper pair is from the left spin up and spin down. But here the Cooper pair is actually spin down, spin up. So we switched to fermions, and that of course brings a sign change. Simply the fermionic wave functions are antisymmetric, which means that if I change the order of 2 fermions, I need to put minus. And if I again write the proper formulas for the perturbation theory and so on and so forth, I find that the magnitude will be roughly the same, not exactly the same, but say on the same order. But there is an important difference, and the difference is that actually I pick minus. So this is the result of the calculation. So the Josephson current will follow this first Josephson relation, meaning that there is a prefactor which I call critical current times sine phi. But this critical current, as it turns out, can be also negative. So for U0, it's always positive. This is kind of a singularity, which is just an artifact of the perturbation theory. So there would be a strong resonant enhancement simply at the resonance of the level with the Fermi energy. But if there is finite U and even infinite U, it turns out that actually the supercurrent changes signs, which here is shown by change of the sign of the critical current, at the positions where the occupation of the dot changes. So here it's like 0 occupancy, I go to single electron occupancy, and IC goes negative. And if there is double occupancy, then it becomes positive again. For infinite U, there is no regime of double occupancy, so I basically just stretch kind of this part. So there is positive for no electron and negative for single electron. This is called 0 pi transition, and this is called pi junction behavior. And it goes almost 40 years back or 35 years back when kind of this calculation was first done. So to speak, the pi junction, there are like 2 explanations. Say one is that obviously to get negative critical current is something like having positive but shifting the phase in this Josephson relation by pi. Or alternatively, if you look at the Josephson junction, due to this tunnel coupling, it actually has a phase-dependent energy, and the ground state typically is at the phase difference 0. But if you have the negative critical current, then it actually turns out that the ground state of the junction will be when the phase difference, the phi, is pi. That's why it's called pi junction. And by the way, there are some proposals of qubits, and this goes back like 20 or maybe even more years, which use the pi junctions somehow. So there are like at least 2 architectures which were suggested. So one is sort of within the dot, that's what I've shown you previously. And an older one is that you actually use more junctions, and some of them should be pi junctions. So Oh, it's probably okay. Okay, so this is pure theory, but this theory was brought to practice roughly in 2006, 2005, where actually 3 experimental groups performed experiments in which they did show the pi junction behavior. So the one which was published first is the group in Delft. And what they used was this semiconducting nanowire, which was this junction was done in here. It was put into a bigger squid loop where there is a reference junction with large critical current. And so it served as a probe of this junction, which is shown in here. So there is this semiconducting nanowire, and there are some gates which sort of close the dot. So they pinch off the tunnel coupling, so to speak. And I think that they also, not I think, but I'm sure they also use the gates to gate the on-site energy, the Xi, which I mean, it's this guy in here. And they were able to measure as a function of phi the Josephson current. This is what's shown in here schematically, meaning their magnitudes. And since it's a squid setup, they were also able to observe when the kind of the phase changed, and they really had the critical current, including its sign. And this is the result of the experiment. So what is here is this gate voltage. So what you see is twice the repetition basically of this picture, because by the gating for this semiconductor nanowire, you can hit 2 single particle levels, but they are well separated, which means that you have like the scenario repeats twice, and actually it can repeat even more times simply. But what is important is that you see that there is this switch from the positive to negative critical current. So zero pi behavior. The fact that it's not an abrupt one is, first of all, it's of course at finite temperature, and second of all, if the tunnel coupling is finite, it's not so small as was assumed in the previous calculation. That broadens this transition as well. Another experiment, more or less simultaneously done, was done in a group of Wolfgang Wönsdorfer in Grenoble. It's a similar setup, similar but not the same. Again, it's a squid, and they used a single carbon nanotube, which is kind of put here over this whole range. And you see that this is like half a micron, okay? So the carbon nanotube is really long, several microns long. There are 2 Josephson junctions in here and in here. Each of them is a stretch of carbon nanotube of almost half a micron. And basically now you have like 2 more or less equivalent Josephson junctions which have this zero pi behavior. So in Delft, there was just one, and there was a reference, a simple Josephson junction, sort of the conventional one. Here you have these 2, say, unconventional ones. But what you can see is that you can play with both of them, because these are exactly the gates which tune this on-site energies. And you see in here that actually one can go by the gate voltages, say from 0 to pi in one of the dots, and 0 to pi in the second dot. So you can even get to the 0, but it's actually twice pi in both of the dots and so on. So they could play quite nicely. Here you see again, it's the magnetic field dependence, so basically phase difference dependence. You see that the blue and the red are more or less harmonic, and you see here exactly, so this was the 0 phase with high amplitude, and you see pi phase, which really has minima, where the 0 phase is maximum. So this is clearly the pi shift, which is really, and these are the measured data. You also see that close to the transitions, these are these 2 curves, the red and green one, that this is quite strongly anharmonic. And also the magnitude is much less. So this is sort of the experimental phenomenology. And finally, there was a third experiment, and I was involved in that one because I was a postdoc in Copenhagen at the time. And the local guys were performing the experiment. And the major difference from the other 2 experiments is on the negative side, this was not a squid setup, meaning that they would not actually see the say negative critical currents like here. they can't see because it's not split, so they just see absolute value of the supercurrent, so to speak. But there was a big advantage. The big advantage was that our guys, before they really performed the experiment, they went to Quantronics group in Saclay in Paris, and the Quantronics group at the time was already for over a decade working on some like really nanoscopic Joule junctions and qubits and stuff like that. And they had a technology for controlling the dynamics of the junction. So the junction is shown schematically here. In practice, it can't be seen, but actually in practice, again, there are electrodes in here. There are the pads for growing a carbon nanotube. So there is a carbon nanotube which you can't see, which again lies somewhere here. And the quantum dot is at the cross section between these two electrodes and the carbon nanotube, like in Grenoble, just this is a different scale. The reason why it's a different scale, because what is shown in here are these resistive golden wires, which are shown in here, which were deliberately designed in such a way that the junction is overdamped. So the phase dynamics is overdamped. It was not the case in the previous experiments, or at least there it's not known in which regime it exactly is. And the problem is the following. What they claim that is IC here is actually not IC. This is a switching current of their setup. And the switching currents and the critical current can be quite different. So they got qualitatively the zero pi behavior, so I think everyone is happy. But actually, here it's like half of nanoamp. And that can be, order of magnitude less than the true IC. And I will just show very briefly in our setup. So what our guys did, okay, so these are the current voltage characteristics of our junction, or maybe I should say Copenhagen junction, because I was involved in the theory, not in the experiment, of course. So these are the current voltage characteristics for different gate voltages. So these are like 3 different experiments, and what you can see is that on some curves you have this type of kink. Actually, it's not superconducting branch, because that would have to be vertical. It's not vertical. This is called a diffusive or diffusion branch. And you see that this kink has a different size. So here it's, say, relatively big compared to here, where it's much smaller, and here it's basically absent. You also see the magnitude. So here you would say that it's like 0.05 nanoamp, and that you would call maybe the critical current. But as a matter of fact, for the overdamped junction, there is a theory which goes back to 68. It's so-called Zilberman-Ivanchenko formula, which is used here. It contains modified Bessel functions of complex order, which is kind of beautiful mathematically. Nevertheless, it exists, and if you ask Mathematica, it tells you what it is. That's no problem. And we use this formula for really fitting these curves, and you see that these lines are really fits of these curves. And I just want to draw your attention to this, because what is shown in here is the IC which was extracted really from these curves, from this fit. And while here you would say that the critical current was, say, 0.05, as a matter of fact, the fit gives 0.65 nanoamp, which is 13 times more than what you would guess here somehow. So really, it's very, very important, and it just shows that the kind of the fitting of the phase dynamics is absolutely crucial for getting really the microscopic characteristics of such junctions, which means the critical current. On the other hand, simply we just get the absolute value of the critical current. We don't see the negative critical currents, because that sort of, there is no chance to see it from IV curve. These are the experimental results. What's shown in here, I will just stress 2 panels. So this is the extracted absolute value of the critical current. And you see that there is like crossing of zero in some sense, which are these curves. So actually in the first round, the experimentalists ignored those curves. But those curves actually make the whole story, because they show that there is actually crossing of zero. That was kind of funny. You see, if you believe that this should be negative, you basically see zero pi transition again. Here are the normal conductance data. They are achieved very easily. You put some not very big magnetic field, you kill the superconductivity, and then you just measure the sort of Coulomb diamonds of this quantum dot. You see that these are not kind of sharp Coulomb peaks. This is more like Kondo stuff. Anyway, the peaks are positioned at the switching of the occupancy of the quantum dot, and that's important in the sense that we see that actually the pi junction transition is not exactly at this point. While in this co-tunneling approximation, it was exactly the point of switching the occupation. Here you can see that it goes a little bit inwards into the pi phase, so to speak. And here there was a very primitive theory, I must say. It's something which technically is a broken Hartree-Fock approach. It's fundamentally wrong in many ways, but it was good enough for us to just show that this kind of turning of the transition point inwards is actually sort of an effect of the finite tunnel coupling, which was pretty much what we were able to achieve at that point. Because I should say that at that time, there was no theory which could really give us the prediction for this data. And not only analytical one, but not even the numerical ones. So both the quantum Monte Carlo and NRG, which are basically routinely used now, were developed around 2010. And we took one of them, which was the quantum Monte Carlo. It was group of Assad in Würzburg. At the time, his PhD student was David Luiz, who actually worked on these data. And we managed quite well. So what was done was this really, quantum Monte Carlo is really a very heavy tool, I must say. NRG with one-day calculation is nothing. I mean, QMC is probably still like order of magnitude worse than that. But anyway, you can do it if you are persistent enough, and for that you really need a supercomputer, that's for sure. And what David did, so first of all, he fitted this normal conductance data. And I think we just worked on, I'm not sure if it was this one or this one, but this we can look here. Okay, I'm still not sure, but one of them doesn't really matter so much. So first he fitted the normal conductance curves. And typically what one needs to fit are these tunnel couplings, the gammas. They are very difficult to get from the experiment somehow directly. Like the U is pretty clear, the gating is also pretty clear, but gammas are difficult. So he needed to fit the gammas, and he did it by fitting simply this normal conductance curve. Then, with no further fitting parameter, he calculated the critical current, which is shown in here. And so the blue dots are the experimental data, and the red curve, which is actually just connecting the quantum Monte Carlo dots, are the quantum Monte Carlo results. And okay, it's a matter of taste if you think it's good or not, but I can assure you that this is by far the best data for such a type of system, which is still today available. It's really pretty hard to make those experiments. So several further experiments were done by different groups, but none was actually able to achieve this nicely resolved zero pi transitions. And also there was, we tried because at that point in 2012 or 11, there was another experiment available, and we gave up because simply it was not possible to match it with the theory by any means. It was completely off somehow, and probably something went wrong in that experiment. So I mean, this is still like the best available experimental data until today, which on one hand is nice that the guys in Copenhagen were so extremely good. On the other hand, it's a bit worrisome that no one can reproduce it until now. But I do believe those data. So the conclusion of this thing, which was published in PRL eventually, is that first of all, this quantum Monte Carlo is really now available as a tool for analyzing the experiments, but it's a bloody expensive tool, I must say. So that's not something you want to do on a daily basis. But there is one more thing which is maybe even more important, because as I told you, it was 0.5 micron long section of a carbon nanotube. And you describe it by a single impurity Anderson model, whose Hamilton I'm just gonna show on the next slide, which is extremely primitive. It has just few parameters. We don't care at all about, you know, physical realization, actually, how the metal is deposited on the carbon nanotube. You don't care about anything. And you have just some 5 parameters, and still what this study showed is that with this primitive model, you can get more or less semi-quantitative description of this experiment. And okay, this is not the only evidence. Actually, there is much more evidence from the normal state cases that this single impurity Anderson model is sufficient for many of these nanoscopic experiments where you have effective quantum dots in, say, carbon nanotubes or semiconducting nanowires. Not all of them can be described by this model, but actually surprisingly many. And it's been really tested heavily in the normal cases against the Kondo features, which are very fine and subtle, and they simply fit. So this is kind of the king of the ball, so to speak, or queen of the ball, I should say, maybe. So this is the model, and it's Hamiltonian. So the dot is, in this respect, just a single particle level, which is spin degenerate. Of course, if there is a magnetic field, you can add a Zeeman term. That's not a problem. But the good thing about these experiments is that you don't need magnetic fields to achieve the 0 pi transition. Actually, there are kind of heterostructured Josephson junctions, which are on a different scale. It's more like micrometers. And I think it's done in Twente, for example, or in Tübingen. Which have IC in the range of microamps, where actually by some epitaxial approach you change normal metal and ferromagnetic, and you get pi junction behavior as well somehow. But that's a different length scale, and simply you use magnetic fields. Here actually you don't use magnetic field, you use this correlation effect by the Coulomb interaction, this U-turn, which actually does it for you. The downside is that the theoretical modeling is really difficult because it's a correlation effect. Anyway, so there is this spin degenerate single particle level, which is this epsilon, which typically can be gated in the experiment. So it's an experimental tunable parameter, which is good. Then you have this local Coulomb interaction, and this is not tunable. You tune in by design, say. But once you do it, it's more or less fixed. There is very little chance to change it somehow significantly. So that's more or less a fixed stuff. Then we have 2 superconducting leads. We just assume BCS leads. Even with that, it's quite difficult. So we don't need to put high TC or anything like that. It would be more fun, but we have enough fun even now. So what is... No, but that's a natural next step, of course. But I mean, you know, we struggle with this one. So there is probably no reason to struggle even more, so to speak. So this is a simple BCS Hamiltonian. What is important that, as you saw in some setups, one can actually tune the phase difference between them, making reduce some current. So this is reflected here by the phases. And then this is this simple Bardeen tunneling Hamiltonian, which goes back to the 50s. Simply, it's just hopping from the leads onto the dot. And so we have just a couple of parameters. So that's this which can be tuned. This can't be tuned. This is given by the material. The phase difference can be tuned. That's nice. And then this tunneling is usually just lumped into a kind of a composite quantity, which is this gamma, which is like tunneling widths. If it were non-interacting, it would be tunneling widths, or the resonant widths, which is just given by the square of this tunneling coupling times the density of states of the normal state metal. Okay, and just to tell you what this model is about, and Alberta showed to some of you already, so I will repeat it. So this model actually is interesting because it exhibits so-called impurity quantum phase transition. Impurity, that's quite clear. It's not a bulk system as such, or it's not system of bulk correlated impurities. It's just a single impurity coupled to more or less non-interacting leads. That's why impurity. Why quantum phase transition? Quantum phase transition is about some qualitative change of the ground state at 0 temperature. And this is exactly what happens for this system, because for certain parameter range, roughly speaking, if the Coulomb interaction, which gives the correlations, is not too strong, then the ground state is a singlet. So it's non-degenerate, single state, it's a spin singlet. However, if you increase the Coulomb interaction sufficiently, it actually turns out that the ground state is a doublet, meaning that you have a spin degenerate ground state. And since these two states have different symmetry, they kind of can't talk to each other, so to speak. So there is a sharp division line, which is basically line of quantum phase transition. There is still some distinction of the singlet. If the U is, say, less strong, then the singlet, if one looks at it, is BCS-like, meaning it's a combination of 0 occupancy and double occupancy on the dot. If you are still in the singlet case, but U is larger, then the singlet looks slightly differently. Actually, the dot is typically singly occupied, but even if it's singly occupied, it's screened by the electrons in the leads, so that altogether it's still the ground state is a singlet. This is just a crossover line, which is fairly difficult to handle. Of course, typically the experiments are somewhere here to make the life a bit more difficult, but we are able to handle more or less everything. Finally, what I'm talking about is a many-body ground state. So maybe I can switch already to, oh, maybe not, sorry. Many-body ground states. What is seen, for example, in STM experiments are spectral functions. Spectral functions describe single particle excitations. Single particle excitations in this language are Andreev bound states. So these are discrete states which appear in the superconducting gapped region. Then above the gap, there is continuum of states. So that's not so interesting in the sense, okay, there is the continuum. It's a bit hard to get anything out of the continuum. But at the places where you expect nothing because there is superconducting gap, you have bound states. And these are these Andreev bound states or Yushiba-Rusino states. I can't go much into what is the difference. I will hopefully do it at the end of the talk if I get there in time. So Andreev bound states, and actually you can very easily identify if you see these Andreev bound states and some parameter dependence of them, if they cross, then this is the point of the quantum phase transition. And that's simple, and I will show you. These are STM data which are taken from this paper. So these are the Andreev bound states, and you see that they actually do cross. This is their theoretical modeling, and they provide these pictures in here. So again, the Andreev bound states are and this is taken from Alžběta's PhD thesis. What happened? Okay, I don't know. So what's shown in here is we look at the many-body states, which, for example, we can get from the numerical normalization group. So one of them will be the ground state. Let's say that for certain parameter, it's a singlet. Then the doublet is above it. Then there might be yet another discrete state. And then there is this continuum, which is above the gap, so to speak. And the Andreev bound state energy is just the difference between these two many-body states. It's a single particle excitation. So you go from singlet to doublet. And you see that the quantum phase transition happens when the singlet suddenly stops being ground state and the doublet takes its place. So there is this difference. And since the Andreev bound state energy is the difference between these two many-body energies, of course, if they cross, there is no Andreev energy, and that exactly also corresponds to the crossing of the Andreev bound states. And here it's shown, this is taken from this paper. So this is basically what is shown in here, just doubled.
Ja, jeg har fått en tur de stykker fortsatt lakker
Is it a question, Jonas? Is it a question or hello?
Sorry, it was sorry. My micro was for some reason.
Yes. Can you turn it off?
I switched.
Okay.
I switch it
thanks.
off. I will switch it off. Sorry, that was not the intention. No, it was not a question. I
Okay,
was
fine,
listening.
fine. Okay, good. So they show basically the same picture in here. This is the many-body states, and here is kind of the ABS differences, and you see that it really corresponds to the measurement, more or less. You also see the situation when there is the quantum phase transition versus the situation when there is no quantum phase transition. And you see simply that if they don't cross, there is no quantum phase transition. If they do cross, there is quantum phase transition. Okay, so far so good. Here I can be relatively fast because actually Alžběta will speak about some aspects of this. So I think Alžběta actually will tell you a lot about that. So what we do is a perturbation theory in the Coulomb interaction. So there is a non-interacting part when U is 0. This is sort of semi-trivial problem in the sense that it's exactly solvable. One can use Green's functions, which is a standard technique simply. If there is interaction, these are captured by so-called self-energies. One can write the full Green's function. What is maybe interesting is that this determinant actually shows where the position of the ABS states are. But that's just a technicality, and this you will hear more from Alžběta, but she actually doesn't have these figures, as I noticed, which I think are more illustrative. So I will go here a little bit in more details through that. So what we discovered, and Alžběta will explain to you actually more about that, is that if you have a setup, then what matters also is how the tunnel coupling is kind of divided between the left lead and the right lead. And typically, so far, people, if they have suspicion that there is an asymmetric setup, they try to calculate it for the asymmetric setup. We discovered that that's actually not necessary. And this is kind of surprising, that the symmetric setup is actually the most general one. And if you have a calculation for the symmetric setup, then you can get whatever asymmetric setup out of that, which is a bit surprising. Actually, if you think a bit deeper about that, this is sort of equilibrium problem. It's not so surprising in the end, but kind of when you meet it the first time, you say, okay, this is kind of weird, but it's true. It is true, and it's really helpful. It's really helpful because it enables you from one calculation for the symmetric setup to get anything else. So typically, the experiment won't be very symmetric. And theoreticians, of course, they need to pick something, so they typically pick the symmetric one because of its symmetry. So you could say, okay, well, it's nice that I have a theoretical paper with the symmetric results, but the experiment is asymmetric, so it's useless. That's not actually the case. You can just take the symmetric results and by some simple operation, which is explicitly shown in here, you just get the experimental relevant results, which I find very neat somehow. So something which Alžběta did not show, say, we have, say, sets of phase diagrams for the symmetric setup. So these are curves for different U's, and you see simply the range of the phase space, which, okay, it's actually not shown here, but I think this is some epsilon. So this is the gating, and this is the phase difference, the two parameters which you can actually tune in the experiment. So you see the phase boundaries for several U's, and you see that it's the curves are, say, non-trivial, so to speak. And now you come to a setup which is and this is for a symmetric setup. Now you come to the situation when the setup is asymmetric. And it turns out that the asymmetric setup has the feature that it only can access this part of this parametric space. So all what you do is that you cut it, you forget about the rest. And since the phase difference in the asymmetric setup also goes to pi, you just stretch it. And this way you can get from the symmetric setup the asymmetric answer. You can see that you can actually get sort of qualitatively different things in some sense, because, for example, if I cut it here, then I don't even get these curves which can start at the edges. I would only have these ones. And I will show you even a different one. It doesn't really matter what is this quantity. But this is the symmetric curve, and these are the curves for the asymmetric setups, for different asymmetries. And all these points are the NRG data. So each of them took like a day or something like that. So this is a bit expensive figure, so to speak. And I think if you look at it at the first sight, you would say, okay, you know, this is a highly non-trivial thing, and it's probably hard to believe that actually there is a single master curve which actually kind of governs all the others. But as a matter of fact, it is. So the blue curve is the master curve, and all the other curves are just obtained by cutting at the appropriate place. The place is determined by the asymmetry. So you cut it at the appropriate place and you stretch it. And if you look at it, it really works. 4 is like the smallest asymmetry. You cut it somewhere here, you stretch it. 7, you cut it somewhere here, you stretch it. 10, you cut it somewhere here, you stretch it. So all these curves are actually this single blue curve, just cut and stretched. So I think this is very neat. And of course, you know, then it means, as we show in here, that you just need to calculate this curve in the NRG. And all the other curves you reliably get just by this procedure. It's an exact mapping for that model. Of course, the experiment may not be exactly described by the model, but that's a different story. If you believe it's described by this model, this is an exact property. And since I'm sort of running out of time, I maybe won't go much into this, but we made another discovery, and I think that's even more important one. I won't tell you the story behind that, but we studied this 3-terminal setup, so it's a Josephson junction, but we added a normal lead. So this could be STM tip or something else. So it's a 3-terminal setup. And actually, if you just try to give this Hamiltonian to the NRG, you find out that the NRG can't do it. It's too expensive, it's simply too complicated. In principle, it should do it, but you would have to wait for 1 month or more. It's simply not viable. So we were kind of a little bit sad, but then we talked to Guru, which is Rok Žitko and Lublania, whose code we use. And he said, look, but this is weird. I mean, if you have just a single level dot, it should always be possible to substitute by a single lead, but the lead might have a non-trivial tunneling density of states. So I sent Petr Zalom to Lublania. He came back with knowledge, like, okay, this is the way how we do it. But then there is an added value of Petr Zalom in our group, because he noticed that, as a matter of fact, if the dot is at half filling, so it means this kind of single occupancy scenario, which is fairly realistic very often, then actually one can do a rotation of these fermionic fields and completely get rid of the superconductivity. So you go from a superconducting setup where you have these anomalous Green's functions of BCS and so on, to actually a standard single impurity Anderson model, so scalar case, but coupled to a semiconductor. And semiconductor with this density of states, and since this is a 3-terminal setup, it's not 0 here, but it's just this gamma n. But if I have just a Josephson junction setup, I can set gamma n strictly to 0, and there will be hard gap in here. But you see that, okay, there is this gap, that's why it's a semiconductor. And then you have this specific kind of singular at the edges, some are singular, some are actually not, density of states, which are governed by this phi. But it's an immense, both numerically, but also analytically, it's much easier to solve a scalar problem than a 2x2 matrix problem. It may not look like that, but since kind of the entries of this matrix 2x2 are actually functions of the frequencies, it's not so trivial to solve it. And this is a really significant simplification. So that's something that we discovered, okay, relatively recently. We still are not through all of the implications for the analytical calculations, but I think that this has a very, very big potential somehow. And what I just want to demonstrate is that, you know, sometimes it's necessary, sometimes it's not, but being clever and trying to find simpler solutions is in this business fairly crucial, because this can be the kind of the dividing edge between being able to say something and not being able to say anything. On the other hand, of course, it's a bit pessimistic for people like from engineering who simply need some input to go farther. And it may take years to us to actually give some input, which is of course not very practical, but that's unfortunately how the situation is if we are to provide really reliable data. I mean, of course, we can give you some crap, that's not such a big problem, which looks reasonable, but it's not. But if we want to have something really, say, reliable, then it might be tricky. Okay, since we are not experts on perturbation theories anyway, I will probably be relatively fast. So what we did is that we just cranked up the standard routine, which is perturbation theory. The lowest order is Hartree-Fock. Hartree-Fock is actually the self-energies are frequency independent. They are just numbers, so that it's relatively simple. Hartree-Fock was done many years before us by various people, but they did what I told you. It's this spin symmetry broken Hartree-Fock, and we know that this is just wrong. I mean, Hartree-Fock or mean fields in general simply tend to give spurious phase transitions. So to get a phase transition for mean fields is no problem. You know, if you use Weiss field on 1D Ising, you get phase transition, so there is no phase transition there. So that's a problem with mean fields in general. So of course, if you allow the symmetry breaking, you can get spurious results. So we used it back in 2006 just to demonstrate this shift of the zero pi transition and so on and so forth. But it was not kind of a clean calculation. We were able to show that we get the zero pi transition even without this spin symmetry breaking, which was not a priori clear. Moreover, we were able to find analytically this the zero pi phase boundary, and actually by a wonderful mistake, I absolutely accidentally found something which we call generalized atomic limit, which is like a fully analytical formula for the phase boundary, which fits extremely well. And you know, basically all the discoveries that we have here are based on errors. Like the symmetry-asymmetry relation was an error. Nothing else. You know, I made a statement which turned out to be just pure nonsense, but when I thought about, okay, what is so nonsense about it, I discovered that, okay, it is nonsense, but as a matter of fact, there is something about it, and we discovered symmetry-asymmetry relation. This gull, which is really beautiful, was just me doing Taylor expansion in the wrong way. That was basically, so I should not be very proud of that, but that's how it simply happened. And I will show you soon, but before that, we went on and we included the dynamical correction. So it means the second order diagrams. So in diagrammatic language, this is the mean field, and these are the second order diagrams. Since it's superconducting, you see that there are this kind of anomalous diagrams. Doesn't really matter so much. It's limited to zero temperature, zero phase, unfortunately, but it doesn't matter. We are able to get to the edge of the zero phase, which means we get the phase boundary, which is one of the things that we want to get. So it's okay. It's actually a very interesting conceptual problem, but more like really in theoretical physics. So I'm not going to bother you with that. But what I'm going to show is that these things perform extremely well. So this is actually the second order. And again, always the dots are NRG data, so this should be the truth about the model, so it's numerically exact. And you see that these approximations that we have, they are basically just on top, which I think is very nice. And of course, the second order perturbation theory is still numerics, but it takes like a few seconds on a laptop or something like that. I mean, that's, you still need to calculate something numerically, but the numerics is irrelevant there. I mean, this is more or less instantaneous. And you see that we get basically the correct results. Here, the phase diagrams. So once again, you see that this NRG is more or less exactly the same as what we call this dynamical correction. So the second order. You see that the Hartree-Fock is not doing very well. On the other hand, you see that this gull So my mistake is actually almost on top of the curve, which is a little bit, it's not always that perfect, but here it is somehow. And we even beat it a very advanced functional RG method by Volker-Meden. It's a little bit accidental, but this very advanced thing is actually performing worse than our second order perturbation theory. So we are quite happy. Again, here you see it's just a different type of phase diagram in the sense that you look at different parameters. Hard refocus off, otherwise everything else is pretty much fine somehow. We have some papers on this, and there is actually even a code which one can use for with the second order. This I will leave to Alžběta. So this was the phase diagram which I showed before. We were actually able to kind of cover this curve more or less fully in the regime of not so strong correlations and something which is called Kondo regime. And this is in PhysRef applied because Alžběta actually came from a conference where she explained the symmetry-asymmetry relation to experimentalists, and after, I don't know, half an hour of explanation, turned out they have absolutely no clue what she was talking about. Which was like, okay, well, we saw that this was really clear and simple, so maybe it's not. So maybe we should do it even simpler. So we decided, okay, if we want the experimentalists to use our theories, then we probably just really need to give them simple formula, right? I mean, I mean, they are not stupid, but they are not theoreticians, and if they are to calculate something more complicated than just using a formula, they are not so eager to do that. So we provided them with formulas, and we even convinced PhysRef applied that it might be useful, which I take as actually a big achievement, so to speak. Again, thinking is generally an advisable approach. I mean, if you think, you can't make a mistake, so to speak. And the reason why I explained why I'm saying that is the following. The experiment, which I think Alžběta will mention from the Orse group, was interpreted by David Luiz, the guy who did the first calculation using quantum Monte Carlo, which I told you was really expensive. They used quantum Monte Carlo, which is kind of something like this, and they made an assumption that the low temperature behavior, because they wanted to find the critical phase difference and the position of the phase transition, they made an assumption that this will be a quadratic curve. So they calculated these red points. It's really bloody expensive. And then they just took the extrapolation by parabola, and they got here. And they declared that this is the position of the quantum phase transition. As a matter of fact, one can show analytically that it's not parabola, but it's a linear curve. We can go to essentially zero temperature with NRG, and actually the correct position is here. And okay, maybe it's not such a big difference, but to get to this wrong position took something like, I don't know, 10 or 100 times more effort than getting to here. I think that's more important. The fact that they are 10% or 20% off is not such a big deal, but the fact that they spend 10 or 100 times more effort on getting to this point, I think is more serious somehow. And simply, it was a wrong assumption. If you do a little bit of analytical work, you find out that simply this must be linear, so you would do better extrapolation, not parabola, but a straight line. You would probably get closer. And we found out, and I hope Alžběta is going to mention it in more detail, we actually found out a method how to do it without any extrapolation, just from sufficiently low temperature experimental data. It turns out that actually the curves should cross at single point, which is the point of the quantum phase transition, and it's not the point of crossing the zero current simply. Anyway, this I leave to Alžběta. And I think I am actually at the end of my talk, even though I'm not at the end of my talk, but I will spare you of the abstract discussion of the difference between the YSR and ABS states, which is very interesting, but I would say not so relevant for you. And let me just flash this one. Of course, as I showed you, all these qubit proposals used double dots. So we looked at the double dots as well. So this is the setup. And we discovered an amazing thing that is generalized atomic limit approximation, which is my wrong Taylor expansion, so to speak, can be generalized to these double dots as well. And you can make a simple normalization of the pair parameters, and you basically get fully qualitatively and semi-quantitatively correct description of the Andreev bound states, which for the double dots are much more complicated actually, because there are singlets, doublets, and triplets. But you see that basically all this fairly complicated phenomenology of the Andreev bound states of the double dot is actually perfectly recovered by this extremely simple generalized atomic limit. And I think this is what, we are always a bit nervous when we use it, because we know that this is kind of a hack in some sense. And what is very embarrassing, we can't really derive it. This is one of the, maybe the only instance which happened to me that the result, it's correct, but you have no clue why. Usually it's the opposite. But here simply, and we've been trying for like 6 years and we simply can't prove it. But it works amazingly well. And of course, this is something which can and should be used by the experimentalists for a fast design of the structures. And then, of course, if you, with this simple approach, you say, okay, this looks like a promising setup, then I think that it's time to go and run NRG to get, say, more detailed, more numerically exact, and so on. But if you were to scan the whole parameter regime for double dot, where you have, I don't know, 10 or 12 parameters, then of course you are gonna burn your supercomputer. And there is actually no need for that. It's better to use this heuristic approach, which should position you correctly, at least roughly, in the parameter space. And then, of course, you can use NRG or quantum Monte Carlo to really zoom in and try to understand in far more detail and much more reliably, of course, what is going on in this specific parameter range. But for a fast scan, I think this is what one can and should actually use. Okay, and this is conclusion. And since I'm kind of behind the time schedule, I just leave it up to you to read them. And thank you very much for your attention.